Testing. 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 Testing, testing, testing. Testing. Testing, testing. Testing. All right. It's working. Okay, welcome to another WhoPost stream. Today we're going to be looking at a paper. This is recommended by a Discord channel member, but it's also been making the rounds on social media. So, you know, it's got great visuals. It's basically a generative video paper. It's called Rerender a Video, Zero-Shot Text-Guided Video-to-Video Translation. This is the actual project page. So often papers will have obviously the paper, which is a PDF, but then there also generally is now this github.io website, which is originally comes from this Nerfies IO page. Yeah, I think this might have been one of the first ones, but the Nerfies had this really great website with these little auto-playing videos and GIFs, and then since then it feels like it's more and more you see papers that have a very nice website with these visuals. Okay, so this is kind of what we're looking at. We're looking at some kind of style transfer that seems to be guided with text. Looks very clean. There's not a ton of flickering, to be honest. The alignment seems kind of there's still a little bit of like an uncanny effect whenever you look at actual humans. But here we go. Here's the architecture kind of diagram. It looks a little bit complicated. You have a lot of different moving pieces here, so it might actually just be really over-engineered, but the effect does seem to be there. Yeah, look at this. So this is kind of just frame by frame with a control net, and then this is probably their method. So there's some kind of temporal consistency being added. You can see kind of the flickering there. Yeah, this is very clean. Here we have, I guess, comparisons against a bunch of other approaches: Fate 0, Vid2Vid 0, PXI2 video, and then Text2Video 0. So it does kind of look like they're significantly better, but obviously these are generally cherry-picked, so it's hard to say. That's a nice little anime. Maybe in some amount of time you'll see my little anime face, you know, rather than my face as you see it right now in the YouTube channel. Maybe I make it look like a little anime Hugo or a little Van Gogh Hugo, you know. That would probably be better, probably get more views. Cool. So that's the little project page. Another thing I've kind of started using is the Hugging Face papers. So this is something that was made by this guy, I think AK, who used to post papers on Twitter, but now they have this, I guess they got hired by Hugging Face. I don't know exactly what their relationship to Hugging Face is, but they now have this papers section on Hugging Face where you can basically go and it's papers, and they're also upvoted, so you can kind of see which papers are the most popular. And that's kind of why I ended up on this paper, is I was going backwards, and you can see here, Rerender a Video, 83 upvotes. So this has been a pretty popular paper. But yeah, there you go. This is the actual paper though, so let's go ahead and pull this up. You got Rerender a Video, Zero-Shot Text-Guided Video-to-Video Translation. So it's not text to video. You're starting from a video and you're ending in a video, right? It's text-guided, which means that you start with a video, you give it a piece of text, and then it turn it into a new video. So you see here, this is, I guess, the original video, and then you add this text, condition whatever they're doing on that text, and then you get this new video. Zero shot means they're not going to be doing any additional training. So No pushing of gradients. Coming from S-Lab, Nanyang Technological University. I haven't actually heard about this one. Let's actually look that up. Nanyang Technological University. So this is Singapore. That's a pretty badass building. Lots of green. I like that building. Top universities in Singapore. Probably good at everything, but okay. Let's go. Large text-to-image diffusion models have exhibited impressive proficiency in generating high-quality images. Is that the best university in Asia? What are the best? Let's ask ChatGPT. What are the top 5 technical universities in Asia? Tsinghua, yeah, I know this one. Is this the same thing? NUS, National University of Singapore. Nanyang Technological University. Peking University, Tokyo Institute of Technology, Korea Advanced. So it might be this one. Yeah, rankings may have changed. They probably did change. I don't know. Okay. Text-to-image diffusion model. So this is your stable diffusion, which goes from text into image, but obviously there's a huge amount of different diffusion models. Midjourney is also a diffusion model. When applying these models to the video domain, ensuring temporal consistency, so consistency across time, right? So the problem that we saw here, right? This is a lack of temporal consistency. See how this kind of like flickers a lot? That's that temporal consistency. Remains a formidable challenge. This paper proposes a novel, zero-shot, text-guided. So novel just means it's new, right? So obviously this is new because just look how complicated this is. Nobody else has done this weird, complicated thing. So one way to get novelty is to just do something incredibly complicated and intricate. Zero-shot means that obviously they're not pushing any gradients. They're just using the models as is. Text-guided means that there's text that is being used to condition something, in this case, translation of one video to another video. And framework just basically means it's a code base. It's a technique. To adapt image models to videos. Okay, so the way they say this here, it actually probably is agnostic to the text-to-image diffusion model, so you can probably use it with your own image models. The framework includes 2 key parts, keyframe translation and full video translation. Keyframes are important frames. So the way that I think the original meaning of the word keyframe comes from animation. Back when people actually used to do old school animation, they would have basically, you don't move the entire joint in like a little animated pixel or Pixar character. You would basically have one keyframe here and then one keyframe here, and then the software would interpolate between those. So I think that's the original meaning of the keyframe. It comes from animation, but basically you could think of it like if you have 30 frames per second times whatever 2 minutes of video, there's specific frames in there that are the keyframe. The first part uses an adapted diffusion model to generate keyframes. Okay. So it'll go through and at a coarser resolution, it'll generate specific frames with hierarchical cross-frame constraints applied to enforce coherence in shape, textures, and colors. Okay, hierarchical basically just means different levels. Cross-frame, I think here they're referring to within the different keyframes. And it sounds like for the keyframes, they're going to try to ensure shape, texture, and color. So how long is this video here? This video is maybe, I don't know, like 10 seconds long. So maybe they have keyframes at 2, 4, 6, 8, 10 seconds, and then they're going to make sure that the colors and the shapes between all of those are the same, and then they'll probably go at a much finer resolution and then kind of make the temporal consistency better. So there's going to be this kind of hierarchical approach of coarse time resolution and then finer time resolution. The second part propagates the keyframes to other frames with temporal aware patch matching and frame blending. Patch matching, probably going to be little chunks of the individual frames that are made more consistent with each other. And then frame blending. Maybe you create intermediate frames by blending two adjacent frames. Our framework achieves global style and local texture temporal consistency at a low cost without retraining, right? So it's zero shot, right? Here you go, zero shot. So that means no training or optimization. I think there is some optimization, right? If you're doing patch matching and adding constraints to enforcing, like, that's a type of optimization. So I don't know about this no optimization. The adaptation is compatible with existing image diffusion techniques, allowing our framework to take advantage of them, such as customizing a specific subject with LoRa. LoRa is low-rank adaptation. It's a type of fine-tuning. You could think of it as a little extra... it's basically changes to the weights of your neural net that you can basically apply, and it makes your neural net good, or it transfers your neural net to a slightly different, in this case, style. So I think whenever people use LoRa's in Stable Diffusion, they have LoRa's for specific styles, like anime style or Pixar style or something like that. And introduce extra spatial guidance with ControlNet. ControlNet is kind of like LoRa in that you're basically training this extra little part, except in LoRa, that extra little part ends up getting basically added to the model, but in ControlNet, that extra part basically receives, we're pulling it up, ControlNet, neural net. Yeah, so in the ControlNet, you have your original neural network, which is going to be the Stable Diffusion, and then you basically have this extra little ControlNet module, which receives a conditioning here, this C, and that C can be something like, for example, this edge map, right? So you take this edge map, you feed it into your ControlNet, you put some text, and then now you have a way to control, hence the word ControlNet, the output of a diffusion model. So extensive experimental results demonstrate the effectiveness of our proposed framework over existing methods in rendering high quality and temporally coherent videos. Code will be released. Okay, good to know. You know, there's a lot of, the speed of research is so fast now that there's not even enough time to like release the code before people read the papers. So, oh, they have a little Hugging Face demo. Drop video, and then you have to run it. That's pretty nice. Rerender. Can I look at the files? What do they got in here? Environment YAML. Oh no, Omega Conf. Dude, this is a config management tool that's like absolutely heinous. Got FFmpeg, that makes a bunch of sense. Implementations, that's augmentation library, right? Implementations. Yeah, this is a image augmentation library, which is kind of weird because they don't do any training, right? Without retraining. So why would they need a dataset augmentation library? It's a little weird. PyTorch Lightning, which is kind of like a framework built on top of PyTorch, is very popular for distributed setups. What else you got here? Transformers, of course. Safe tensors, which is a way of saving and giving people pre-trained models that doesn't have this security vulnerability of basically loading Python objects. And Torch Vision, CUDA Toolkit, these other ones seem fine. Okay. And then here you go, it's literally, they have the just ControlNet, just copy pasted in here. Pretty cool. All right, let's get to it. Introduction. Recent text image diffusion models such as DALL-E 2, ImageGen, and Stable Diffusion demonstrate exceptional ability to generate diverse and high quality images. Based on it, a multitude of image editing methods have emerged, including model fine-tuning for customized object generation. So model fine-tuning here, things like LoRa, or the newer version of LoRa that we actually read on the channel, it's OFT, orthogonal fine-tuning. That one actually seems better than LoRa, but it's really, really new, so we haven't really seen it appear in the papers yet. Image-to-image translation, image inpainting, object editing, these are all just different tasks. These applications allow users to synthesize and edit images effortlessly using natural language within a unified diffusion framework, greatly improving creation and efficiency. Video content surges in popularity on social media platform. I mean, are we going to see video content in VR headsets, or are we going to see a new type of video content? This is something that I think people don't talk about, but I feel like as we start getting more VR headsets and AR headsets, 2D video might actually become kind of a legacy modality, right? I could see kind of 3D video, like Nerf videos might actually become the new modality that people want to see. So we might be near the end of the video as a modality. A critical challenge, the direct application of existing image diffusion models to videos leads to severe flickering issues, right? This lack of temporal consistency. Researchers have recently turned to text-to-video diffusion models and proposed 3 solutions. Okay. Training a video model on large-scale video data. That just doesn't sound like a good idea at all, because large-scale video data not only is incredibly expensive to gather and collect and clean, but then training a large model on that is even more difficult, which requires significant computing resources. The redesigned video model is incompatible with off-the-shelf image models. The second solution is to fine-tune image models on a single video, which is less efficient for long videos. Yeah, anything where you're basically fine-tuning or training, not a good idea, because it's just going to take so much longer, right? Which I think they're kind of setting you up for that, right? They say, okay, there's 3 different ways to do this, and the first way involves pushing gradients, and that sucks. The second way involves pushing gradients, and that sucks. So you can kind of see them teasing the third way, which is not gonna, third solution involves zero-shot methods, right? So now they're gonna basically argue that anything that you can do zero-shot is gonna be way better because you don't have to do any additional training. During the diffusion sampling process, cross-frame constraints are imposed on the latent features for temporal consistency. Ooh, okay, so cross-frame here, cross-frame constraints, this is the actual constraints that are gonna be driving the generation, right? But interestingly here, the way that they set it on the latent features, so these constraints are not going to be in image space. It sounds like they're actually going to be in latent space, which is actually a great idea because it means you can do it faster. The latent space is usually smaller and easier to deal with. Latent space diffusion models. Yeah, so let me see if I can find a good picture here. What's a good pic of a latent space? Yeah, so this is the, you can think of it this way. So there's encoders and decoders. So basically, inside a lot of machine learning systems, you have this kind of encoder-decoder pattern where you have something, a raw, kind of very large data modality, such as images, and then you can encode it into these little, here they show them as like a little Rubik's Cube looking thing, but this is basically a latent space, right? And this latent space is smaller than the image space, right? So when I say latent space, think about these little Rubik's Cubes. When I say image space, think about the images. And doing things in the latent space is cheaper because they're smaller, right? And a lot of diffusion models work in latent space for that reason. Okay, the zero-shot strategy requires fewer computing resources and is mostly compatible with existing image models, showing promising potential. However, current cross-frame constraints are limited to global styles and are unable to preserve low-level consistency. Yeah, so I think this is kind of where they're going to tease their hierarchical approach. So at some point you have to decide, where are these cross-frame constraints applied? Are you applying it to frames that are seconds in between, or are you applying it to frames that are adjacent, right? So it makes sense that you might want to apply slightly different constraints depending on the distance between those frames. Achieving successful application of image diffusion models the video domain is a challenging task. It requires temporal consistency, cross-frame constraints for low-level consistency, zero shot, no training or fine-tuning, and flexibility, compatibility with off-the-shelf image models for customized generation. I like the way that they're like kind of phrasing this, right? It's like they're almost like, the problem in the world is exactly what we're offering. You know, it's like, I like that these three things are the three things that are basically seem to be important for this paper, but they're kind of making it seem like they're the only three things that matter, which is a little bit weird. Image models can be customized by fine-tuning on specific objects. Show two examples. In this paper, we employ zero-shot strategy for model compatibility and aim to further solve the key issues of the strategy in maintaining low-level temporal consistency. To achieve this goal, we propose novel hierarchical cross-frame constraints for pre-trained image models to produce coherent video frames. So here's your novel hierarchical cross-frame constraints. So a hierarchy of cross-frame constraints. Pre-trained image models. This should be pre-trained generative image models, right? So you can basically drop in your image gen, you can drop in your DALL-E 2, you can drop in Stable Diffusion, and it should basically work the same. Our key idea is to use optical flow. Optical flow is this way of describing the motion of things in a picture, right? So we've had some pictures of these before, but for example, something like this, right? You have a picture of people moving. This is actually a terrible thing. Okay. Let's do more of this one. Yeah, this one makes more sense. So you open image in new tab. There we go. So you can see here how this is a field, right? So there's basically a field of vectors here, right? For every single point on this field, there's a vector, and then you can see how the vector tells you the movement of that particular set of pixels, or ideally the semantic object behind that set of pixels. So you can see here how this the car is moving, but the floor is not moving. This person is moving. So optical flow tells you what is moving and in what direction. So here, optical flow for an autonomous vehicle. Of course, it kind of looks like the Star Wars when you like zoom in, right, where the center isn't moving, but the outward part of the image is moving away. And generally it's color coded, so whenever you see this is also optical flow, even though it doesn't look like a bunch of vectors. But the way that they color coded, the red, green, and blue is basically the angle of the vector. So whenever you see this, basically it's just optical flow for every single pixel, where the color tells you the direction of the optical flow. Pretty smart that they're utilizing optical flows. Yeah, I mean, it's a good idea. The problem is that optical flow isn't something that you just know. You have to basically get the optical flow. So how are they going to get the optical flow? They can calculate it by basically taking frame 1, frame 2, frame 3, and then just kind of like, there's different ways of getting the optical flow, but it's not perfect, right? There's no ground truth optical flow that like actually knows what's in that video and gives you the exact perfect optical flow. Like, all ways of getting optical flow are just approximations. So we'll see exactly how they get the optical flow, but it's a good idea to use that within this hierarchical cross-frame constraint. With the previous rendered frame serving as a low-level reference, and then the first rendered frame acting as an anchor to regulate the rendering process to prevent deviations from the initial appearance. Okay, so they have previous rendered frame, and then current frame, and then first rendered frame. So basically you have I guess the first frame in the video, then you have the current frame in the video, and then you have the next frame in the video, and the one right around it. So you have this kind of like local area around a current frame, and then you have these keyframes. Hierarchical cross-frame constraints are realized at different stages of diffusion sampling. So diffusion in itself is not a single process. Diffusion usually takes a couple steps to do, right, on the order of 10 or even 100 steps of diffusion just to generate one image. So here what they mean by different stages of diffusion sampling. They mean even within the diffusion process, you're going to have these constraints acting. In addition to global style consistency, our method enforces consistency in shapes, textures, and colors. The way that they are enumerating these makes me think that they're going to have different consistency terms for each of these. So there's going to be one for all. There's going to be one for shapes, one for textures, and one for colors. At early, middle, and late stages, respectively. This innovative and lightweight, I don't know about lightweight modification. This looks pretty complicated. Both global and local presents our coherent video translation results over off-the-shelf image models customized for 6 unique styles. Okay, so this is the original video, right? And then this is the text that is used to condition the diffusion. And then here you have the general model, customized model. I guess by general model they mean their model, and then, or I don't know what they mean here by general and customized. Customized and control net generate high quality results with better prompt. Our method is designed to be compatible with these existing image diffusion and thus can take advantage of them to strike a good balance between the style and the content. Okay, so let me close out of Slack here just so I'm not like too many notifications. So you usually there's, whenever you're dealing with diffusion models and you're kind of transferring and you're conditioning the diffusion on a specific piece of text, usually there's a weight, like a guidance weight, and that weight tells you this kind of balance between the actual text and then the actual content. So there's a little bit of a human touch here as well in terms of how much do you want the person to look like the handsome Ghibli style versus how much do you want the person to actually look like the person that's in this picture. Figure 1 presents a coherent blah blah. Based on the insights, this paper produces a novel zero-shot framework for text-guided video-to-video translation consisting of 2 parts: keyframe translation and full video translation. Okay, so multi-part optimization here. In the first part, we adapt pre-trained image diffusion models with hierarchical cross-frame constraints for generating keyframes. Okay, so first you generate the keyframes, which is going to be maybe a frame every second or a frame every couple seconds, right? And then in the second part, you're going to propagate those keyframes into the more finer resolution frames, right? And usually you're talking about 30 frames per second for video is pretty standard. Obviously, you can go 60 frames per second. You can even go 120 frames per second. I think around 120 or 200 frames per second, the human can't really tell anymore, which is actually why in most VR headsets, like if you can get to 200 frames per second on a VR headset, that's pretty much everything you're ever going to need, right? There's kind of like a limit to how much a human can even see the difference, and it's somewhere in between 120 frames per second and 200 frames per second. But I think our current technology, usually when you watch a YouTube video, it's at 30 frames per second. The diffusion-based generation is excellent at content creation, but its multi-step sampling process is inefficient. Yeah, so if you were to apply the diffusion model at every single frame, it would be very long, right? Diffusion models are actually kind of slow because they have this kind of like multi-step. There's like one nice picture that I like for this. Yeah, so this picture kind of shows you, right, that whenever you're generating an image from a diffusion model, it's not just a one-shot type of thing where you're basically just going from here, boom, to that image. You have to do this kind of iterative removing of noise, and every single one of these is an inference, a model inference. So if you had to do that for every single frame in a video, it would be very intense. By combining these 2 parts, our framework strikes a balance between quality and efficiency. To summarize, our main contributions are as follows. All right, so here at the end of the introduction section, they have their little bulleted list of contributions. A novel zero-shot framework for text-guided video-to-video translation, which achieves both global and local temporal consistency, requiring no training, and is compatible with pre-trained image diffusion models. This is a great summary. You know, this is literally a summary of this entire paper, but it's actually also the most impressive and great thing that they did, right? There's just so many things here, right? No training, compatible with any diffusion model. It's zero-shot. So maybe there's a little bit of redundancy here. You don't need to say requires no training if you're saying zero shot. And then text-guided video-to-video translation is what they're doing. Hierarchical cross-frame consistency constraints to enforce temporal consistency in shapes, textures, and colors which adapt image diffusion models to video. And then hybrid diffusion-based generation and patch-based propagation to strike a balance between the quality and efficiency. So they're going to be doing something with patches. This is now the second time that they mention patches, so we'll see what they do. But generally, anytime you deal with patches, you have to define the size of the patches and the location of the patches, so you end up having a bunch of extra hyperparameters. And that's something that we saw in yesterday's paper, where they were also doing this patching, but for the purpose of self-supervised learning. But then they had all these extra patch parameters, the size of the patch, the location of the patch, and it ended up being kind of sensitive to the hyperparameters there. So I wonder if there's a sensitivity to the patch hyperparameters here as well. Let's take a little sip of this yerba mate and keep blasting. So when they state zero shot, that means there's no training required? Yes, no training required. Zero shot basically means that right off the bat, which is what you want, right? You don't want to have, because the reason they want to do zero shot is because then they can use any diffusion model that you want, right? You can just plug in your diffusion model and use it. But it's also maybe just to elaborate further, no training required doesn't mean that this doesn't take time, right? Because this is going to be a relatively complicated hierarchical process, right? You're basically going to have to separate the video into keyframes and then run the diffusion on each of those keyframes and then do this temporal consistency on all the different other frames. So it's not like this is going to take one model inference, right? This translating your video from this to this, it's probably, I don't know, if I had to guess, this is probably 5-10 minutes per video easy, depending on the length of the video. So even though you're not spending any time training your model, you're still going to have to, you're still limited by the speed of this kind of complicated hierarchical process. Generating images with descriptive sentences is intuitive and flexible. I agree. Early attempts explore generative adversarial networks with powerful expressivity of the transformer, very popular model architecture. Autoregressive models, which are models that auto-regress, they regress on themselves, are proposed to model image pixels as a sequence with autoregressive dependency between each pixel. DALL-E, this is the OpenAI image generation model. CogView, train an autoregressive transformer on image and text tokens. Make a scene, further consider segmentation tasks as condition. Recent studies on diffusion models for text-to-image generation where images are synthesized via a gradual denoising process. This is what diffusion is really just doing. It's just gradually denoising. It's removing the noise gradually. DALL-E 2 and ImageGen produce, I think ImageGen is Google's paper. Yeah. Photorealistic text-to-image diffusion. I wish there was a back. You know, I wish I could just return so I didn't have to scroll whenever I do this, but as text encoder to better align the image with the text. So whenever you have anything that's basically using text to condition, generally you have some kind of encoder that's turning your text into a embedding or vector that represents the meaning of that text, and then your generation is actually being conditioned on that text, that encoded text, not the actual raw text. Cascade diffusion models for a high-resolution image generation. Cascading just means basically doing one thing and then another thing and then another thing. So, for example, you might have one diffusion model that's smaller, and then you have an high resolution one and then a high resolution one. Cascade actually comes from like a waterfall. I think it literally is the word for a waterfall. Yeah, a steep, usually small fall of water. Glide introduces classifier-free guidance to improve text conditioning. This is this idea of the guidance weight that I was kind of mentioning, where depending on how strong you want the text to be, right? Do you want the text to kind of very strongly impact the original or the image diffusion, or do you want the text to be just a little bit more subtle? So kind of the strength of the text. Instead of applying denoising the image space, latent diffusion models use the low resolution latent space of a VQ GAN. This is a vector quantized GAN, right? So a GAN where the latent space has been quantized into a codebook to improve the efficiency. We refer to for a thorough survey. How does that work? Wouldn't no training potentially produce a lower valued result since it might not fit for your specific use case? Yeah, I think that you can use LoRa, and so right, like you might have a image diffusion model that works for a specific use case, right? Like let's say you took Stable Diffusion and then you trained a LoRa for that Stable Diffusion that works very well with some weird depth camera that you're using, right? You could then take that diffusion model that has that LoRa for the depth images that you want, right? Your weird specific modality, and you could apply this technique with that model. So if you want to take a diffusion model and fine-tune it for some specific style, you can use that fine-tuned diffusion model and then just plug and play it into this framework. So this framework doesn't care if you have fine-tuned your Stable Diffusion. They keep mentioning efficiency. I hope they mention the specific GPU memory requirements in later parts. Yeah, generally, as soon as you have video, it's not efficient. Like that's the secret, is that video is just such a crazy modality. You know, you have so many images, so many frames that generally anything you do with video is not efficient. It's incredibly slow. Dream Booth learns special tokens that capture novel concepts and generate related images. LoRa accelerates fine-tuning and learning low-rank weight matrices added to the existing weights. ControlNet fine-tunes a new control path to provide pixel-level conditions such as edge maps and poses, enabling fine-grained image generation. Our method does not alter the pre-trained model, thus it is orthogonal to these existing techniques. Yeah, this is kind of what I was trying to describe, Keyshawn, so sorry if I confused you with my terrible wording, but you can apply ControlNet and LoRa separately, orthogonally from this technique. Orthogonal basically just is this, right? It's a right angle, so it means that they're independent. Better video translation, okay. Still related work section, so we're still in the related work section. Now we're in a new subsection within the related work section, video editing with diffusion models. For text to video generation, video diffusion models propose to extend the 2D U-net. A U-net is a type of model architecture that basically is very wide, then it gets very narrow, and then it gets very wide again. An image model to a factorized space-time U-net. I don't know what that is. Factorized space-time U-net. Dude, what? Oh, okay, so spatio probably refers to the actual within the image, and then temporal refers to the fact that in a video you have multiple images. So you have this time dimension in the video. So I bet you that what's going on here is that you have a U-net in the time, and then you have a U-net in the image space. Okay, this paper looks gross. ImageGen Video scales up video diffusion model with a cascade of spatial and temporal video super resolution models. Make a video leverages video data in an unsupervised manner to learn the movement to drive the video image model. Although promising, the above methods need large-scale video data for training. Yeah, so this is kind of something that we're talking about in the introduction section, but any technique that involves pushing gradients based on video data is going to be very limiting, just because I just don't feel like video data is great. Tune-a-Video inflates the image diffusion model into a video model with cross-frame attention and then fine-tunes it on a single video to generate videos with related motion. You have all these different techniques here. Edit a video, video P2P, vid to vid 0, precise inversion to preserve the unedited region. These models need fine-tuning. This is kind of why I don't like related work. I think we read a couple papers where the related work was actually in the appendices, and I kind of prefer that because it's like this. I don't feel like I'm effectively using my time here, right? It's like they're just mentioning like 700 other papers that do slightly different things. But really what I'm interested in is this paper, right? Recent developments have seen the introduction of zero-shot methods that operate without any training phase. These methods are naturally compatible with pre-trained diffusion models like Instruct Pix2Pix or ControlNet. Based on editing masks, indicate the channel. Fate 0 blends the attention features. Text video to 0 translates the latent to directly simulate motions. All of the above methods rely largely on cross-frame attention and early step latent diffusion or early step latent fusion to improve temporal consistency. So latent fusion, I guess, here is basically you're looking at the latent space and you're looking at neighboring frames, right? So two frames that are close together, although it doesn't necessarily need to be close together. We will show later, these strategies predominantly cater to high-level styles and shapes, being less effective in maintaining cross-frame consistency at the level of texture and detail. Yeah, so it's kind of interesting how in yesterday's paper we were reading about a self-supervised learning technique where they're basically the biggest thing they were arguing is that the representations that you get from the IJEPA, which is the name of the paper, are high-level, high-semantic representations where they basically ignore texture and detail and focus all their representational capacity on the actual content of the image. And it's interesting that now, today, we're reading a paper where it's actually the opposite, right? It's like you don't care about the high semantic representation of an individual image. You care about the texture and detail. So it's interesting how, depending on what you're doing, the image representations that you want to use are going to change, right? Sometimes you want texture and detail. Sometimes you don't want any texture and detail. Vladimir, factorized spacetime unit sounds like something from an 80s sci-fi. I totally agree with you. And I think that's why they chose that, right? Because you could basically call video like space-time, I guess. It's a little bit of a stretch in terms of the abstraction, but our method proposes novel pixel-aware cross-frame latent fusion, which is non-trivially achieves pixel-level temporal consistency. Okay, now that we're done reading about what other people did, let's actually see what they did. So here, preliminary diffusion models. So preliminary sections explain the basic concepts of the technology. So here, obviously, they have a preliminary section on what diffusion models are so that you can kind of understand diffusion models. And a lot of people obviously skip this, right? So probably already know what diffusion models are if you're reading this paper. So a lot of people will read this preliminary section and then just basically skip it and just go straight to here. But I tend to like reading these because basically you can think of it like you're reviewing diffusion models, and it's kind of like an attempt to say, hey, here's how we think of diffusion models, and it's a competition to see who can explain diffusion models in the most clean way. So let's see. Stable diffusion is a latent diffusion model, right? So it's a diffusion model that operates in the latent space of an autoencoder, D, E, where E are the encoder and decoder. Okay. there's actually a typo right here. There should be a D right here. E and D are the encoder and decoder. So right off the bat, there's a little typo. But an encoder and a decoder, I think I had a picture of this pulled up. But okay, maybe this is okay. Here you go. Encoder, decoder. So the encoder takes your raw image, turns it into a latent. The decoder takes your latent and then turns it into an image. So they basically work in tandem there. For an image I with its latent feature x0, right? So you give your image to the encoder. Your encoder is a function. It's a neural net. A neural net is a function approximator, right? A function takes some inputs and produces some outputs. So here your input is the image, the output is the latent. The diffusion forward process iteratively adds noises to the latent. So the diffusion, whenever you're actually performing inference, you're removing the noise. Whenever you're training, you're adding the noise. So here, your image at time t, right? So you see here how there's different time steps. So here you have time step 0 and then time step capital T. So the image at time step t, or this is actually not even the image, x of t is the latent. So they're doing this in the latent space, not the image space, but you condition it on the previous image, right, or the previous latent. And then here you have this n means a normal distribution. So this is a normal distribution. This is going to be the mean of the normal distribution. And then this is going to be the standard deviation of the latent, or standard deviation of the normal distribution that represents the noise, right? And these alpha terms here, so alpha is a hyperparameter, but basically this is a noise schedule. So generally in these diffusion models, the noise that is added or removed, right, depends on a schedule. So if you are closer to capital time t, you're probably going to be adding noise more aggressively. If you're here closer to capital time, or if you're here at t 0, the noise that you add is going to be generally smaller. So there's a schedule that is dependent on the time step that impacts the noise that is added. So that's what these alphas are, right? They change the amount of noise that is added depending on where in the diffusion process you are, right? And this T here is basically where in the diffusion process you are. Q is the conditional density of xt given gt minus 1. So what is gt minus 1? The fuck is gt? They don't even tell you. GT might be the guidance, I guess. I don't know. Or maybe this is a typo. Yeah, this is another typo. So Q of xt given xt minus 1. So you see this little parallel bar here means given or conditioned on. And here you have x of t, but I think this here they put gt minus 1. I think this should be xt minus 1, right? Because that's just what this equation is saying here. Alternatively, we can directly sample xt at any time step from x0 with q xt given x0 equals this, which is basically the same thing that you have here, except here you see how you have an alpha bar, right, rather than alpha, and the alpha bar is just the cumulative sum or cumulative product here. So this is just multiplying alpha bar 1 with alpha bar 2 with alpha bar 3 all the way to whatever your time step t is. Wow, the highlighting on this is terrible. In the diffusion backward process, a UNet, so this is the actual predicting of the noise, right? To iteratively recover x0 from xt. So when you're actually training, you're going, where's my diffusion model? Donde está diffusion model? This way, right? So you're adding the noise, or removing the noise, or adding the noise. And actually, the way that you remove the noise is you predict the noise and then you remove the noise. So this UNet here predicts the noise. Okay, given a large t, x0 will be completely destroyed in the forward process so that xt approximates a standard Gaussian distribution. Yeah, so this is actually something that we saw in another paper that we read, where it actually turns out that in the implementation of a lot of these diffusion models, the very last step actually doesn't become pure Gaussian noise. Basically, you want this very last frame at time step capital T to be pure Gaussian noise, but it turned out that these people went and they looked at the actual implementation of a lot of diffusion models, and it turned out that they weren't doing that, and the very last frame still had a little bit of information left, specifically the pixel statistics of the original image. So that's not what you want, right? You want the final time step of this diffusion process to be pure noise. Epsilon theta correspondingly learns to infer valid x0 from random Gaussian noises. Once trained, we can sample xt-1 based on xt with a deterministic DDIM sampling. So there's different sampling strategies for diffusion models. There's DDIM. There's also another one called DDPM, I think. But yeah, maybe they talk about why they specifically picked this one. I think this is the more popular one anyways. Okay, so we have equation 3 here. We have x at t-1, the latent at time step t-1 equals alpha at t-1, the schedule for the noise, times x hat t to 0, predicted x0, plus just another alpha dependent term. Here's your actual UNet output. So the UNet is given the latent at time step t, it's given the t, and then it's also given this CP, which is probably the conditioning. Yeah. So this CP is the text prompt. So it's basically the text, but the text after it has been fed into a text encoder and turned into basically a little vector that represents the semantic meaning of that text. That's what this little CP here is. So your noise, it's not just predicting the noise based on the image and the time step, it's also predicting the noise based on that text prompt, which is why diffusion models even work, right? Okay. During inference, we can sample a valid x0 from the standard Gaussian noise xt equals zt, zt equals n of 0, 1. So here you had a normal distribution, right? That's a little bit more complicated here because it's based on this alpha bar, or this alpha, which is a hyperparameter that changes over the course of the diffusion process. But this is what a normal distribution looks like, right? It's centered on 0, and it has an identity matrix for the standard deviation or the variance. Variance and standard deviation are the same thing. They're basically just, standard deviation is the square root of the variance. Variance, standard deviation, one is the square root of the other, I forget. Yeah, the variance is square is the standard deviation squared. So variance and standard deviation are basically the same thing. With DDIM sampling, and decode x0 to the final generated image, I tilde equals dx0. Okay, so once you've finished doing all your removing of noise conditioned on the text, you're eventually going to get some x0, right, which is going to be a latent. So in order to get the actual final image, you're going to need to take your latent and you're going to need to feed it into your decoder, which here is this script D, right? So where's our control net latent space? Yeah, so you're doing everything in this Z space, but at some point you actually want the original image back, so you're going to you're doing everything in this latent space, right, this Rubik's Cube, but at some point you're going to want the original image. So once you're finally done doing all your diffusion, you're going to take that little Rubik's Cube and you're going to feed it into your decoder, and it's going to give you an actual image. So that's what they're saying here. All right, once you're done doing all this crap, you feed your x0 into the decoder, and it's going to give you the final image that you want, this I prime. Okay, although flexible, natural language has limited spatial control over the output. To improve spatial controllability, we introduce a side path called control net. Yeah, so this is a very popular technique. I've explained it a million times, so I'm sorry if I keep explaining it every single time it pops up in a paper. But I'm also trying to make sure that someone who isn't an expert can still watch these videos and kind of understand. Actually, I like this. Look at this. This is a really good picture. So here in this picture, they have the neural network block here locked. So the locked means that it's frozen. You're not pushing gradients into this. So this will be your actual stable diffusion. And your stable diffusion is operating in the latent space, right? So it's removing noise from this little latent vector, this 64 by 64 latent vector here represented as a kind of Rubik's Cube looking thing. And here you have your actual control net, which is a separate, you can think of it like a separate little neural net that's different from the stable diffusion, and it's basically attached. It's kind of like parasitically attached to the stable diffusion model, right? And it receives this Z of t, and then the thing is that it uses it can use different things. So in here they're showing it with a edge map, right, which is basically just a black and white image that represents the edges, and you can get this just with a simple algorithm known as the canny edge detection, which is just some hard-coded heuristic algorithm. But you can also condition control nets on different things, right? Control nets are trained on different types of conditioning. So you have some that work with depth images, some that work with poses, some that work with what are normal maps, probably? I feel like normal maps, segmentation maps. There's different inputs that you can put here, and you're going to have a different control net for different types of inputs. But those get fed in, and then that ends up modifying. So you see, normally if you didn't have this control net, then you wouldn't have this extra stuff that comes in here and modifies it. So your control net is modifying your original neural net. I feel like I'm like not explaining things super clean today, so I apologize. I just need more caffeine. Okay, let's CF be the extra condition. So CF is this, right? It's here it's CI, but it's basically, think of it as basically an additional control signal, such as an edge map. The noise prediction of the UNet with control net becomes this. So not only is your noise prediction network given the latent at time step t and the time step and the text in the form of a text embedding, but it's also now you're giving it the extra control net CF. Compared to instruct pix to pix, control net is orthogonal to customized stable diffusion models. You can have a LoRa with a control net. To build the general shot V2V framework, V2V just video to video, we use a control net to provide structure guidance for the input video to improve temporal consistency. Okay. So that's their little summary of diffusion models and their summary of control net. And now they're actually going to go into their actual technique here. Zero shot text guided video to video translation. Maybe they missed 2 video there. All right, let's look at this figure 3. Framework for the proposed zero shot text guided video translation. We adapt the pre-trained diffusion model, stable diffusion plus control net. With hierarchical cross-frame constraints to render coherent frames, the red dotted lines denote the sampling process of the original image diffusion process. The black lines denote our adapted process for video translation. We apply different constraints at different sampling steps. Here you have kind of a cross-frame attention, adaptive latent adjust, pixel-aware latent fusion, and shape-aware latent fusion. So there seems to be, I don't know what this is, sampling pipeline? We might have to read the section. So you know what, I feel like if we try to read this figure, we're not going to understand what the fuck is going on. So let's actually read this section first, and then once we're done reading this section, we'll go back to the figure. Okay, so given a video with n frames, so a video is composed of a bunch of frames, in this case capital N. and each frame is an image. Our goal is to render it into a new video, I prime, in another artistic expression specified by text prompts and or off-the-shelf customized Stable Diffusion models. Our framework consists of two parts, the keyframe translation and then the full video translation. So I think the keyframe is the coarse resolution, and then the full video is the finer resolution, aka the hierarchical. Or maybe it sounds like hierarchy is actually, there's an additional hierarchy that's applied here. We introduce hierarchical cross-frame constraints into the pre-trained diffusion models to render coherent keyframes, and then the second part propagates the rendered keyframes to other frames with temporal aware matching and blending. Okay. Lots of different moving pieces. Illustrates the T-step sampling pipeline. So T-step sampling, aka the diffusion model, has T steps to it. Following SD edit, the pipeline begins with X capital T. So this is the first image, right? The first image should ideally be pure Gaussian noise. So the for X of T should equal Z of T here. Z of T is a pure Gaussian noise. The noisy latent code of the input video frame rather than pure Gaussian noise. Okay, so I don't know if this is good. They're saying that rather than starting from pure Gaussian noise, we want to start from the original video frame, so whatever the first frame of the video is, and then we're going to basically apply very aggressive noise from that. Yeah, there's definitely a trade-off there, because basically if you start from pure Gaussian noise, you're not going to get anything that looks like the original video, right? And in this case, you're not doing text to video, you're doing video to video. So you need to have some notion of the original video there. It enables users to determine how much detail of the input frame is preserved in the output by adjusting T. Smaller T retain more detail. So if you have less steps of diffusion, less removing of this noise, then you're going to get the original video, right? If you have less of these diffusion inference, which is basically what this T means, is how many times are you doing inference with the diffusion model, then your original video is going to remain more unchanged. We use the first frame as an anchor frame and the previous frame to constrain global style consistency and local temporal consistency. So you have style consistency being used globally, and then you have temporal consistency being used locally. Cross-frame attention is applied to all sampling steps for global style consistency. In addition, in the early steps, we fuse the latent feature with the aligned latent feature of previous frame to achieve rough shape alignments. We fuse the latent feature with the aligned latent feature of the previous frame. So I don't know what fuse here means. There's a lot of different things that could mean. Maybe it just literally means they just like add them and then divide, so it's literally just an interpolation between the latent of the previous and the latent of the current frame. Fusing kind of implies like some kind of concatenation, but in the mid steps we use the latent feature with the encoded warped anchor. So the anchor is the very first frame. That's what they mentioned up here. And previous outputs to realize fine texture alignments. In late steps, we adjust the latent feature distribution for color consistency. So the distribution in the latent space, they probably, I guess, blur it. You don't want the latent space of the video to change wildly, right? But I don't know if that's necessarily true, because I can imagine a situation where the video moves very quickly and then you're going to have different colors. So I feel like these type of constraints, they work for these short videos where nothing really happens, right? But I feel like once you go into longer videos where you have a lot of changing things and the whole kind of content of the video changes rapidly, then I don't know if having this type of color consistency is necessarily a good thing. We will use I, and 0 to refer to keyframes in this section. Okay, so this is only the keyframes. Yeah, that's what I'm saying. I'm sorry, I don't actually know how to say your name because it's in Korean, so I apologize, but I agree. The angle change and the lighting condition changes, so the color shouldn't be consistent. So I think that this color consistency and these kind of like global style consistency is itself a local consistency because that video itself is only a couple seconds long. So I feel like if you had a whole movie, then you probably wouldn't want the same type of what they're calling global style consistency. Hyun Ho. Yeah, this is kind of confusing. So up here they say the video has n frames, but then they use the same exact notation to refer to the keyframes. Right? I feel like that doesn't make any sense. I would have called it I hat or something, or IK or something like that, but every frame is a keyframe is kind of what they're saying there, which doesn't make sense. Style-aware cross-frame attention. Similar to other zero-shot video editing methods, we replace self-attention layers in the UNet with a cross-frame attention layer. So they say UNet here, but the way that they're saying self-attention and cross-frame attention, that to me means like some kind of transformer, right? Transformers are a model architecture that has an attention mechanism in it. And you can have self-attention, where basically the transformer is paying attention to its own sequence, right? Or you can have cross-attention, where in the original transformer, the cross-attention is with respect to two sentences in two different languages. But cross-attention in this case would probably refer to the one frame and then the previous frame, or two different frames. But self-attention layers in the UNet is kind of a weird phrase. Let's see. Is there a UNet that has attention layers? I don't think there is, but let's see. Okay. So when I think of UNet, I think of like kind of like an old school UNet that's basically looks like this. It's just a ConvNet, right? But this actually makes sense. So it does sound like there's an attention UNet. Is this real? Is this hallucinated? Let me see what this looks like. Okay, so an attention UNet is basically just UNet versus attention UNet versus attention res UNet. Okay, so basically there's a UNet that has attention inside of it. I guess that's kind of cool. So that kind of explains that. Layers to regularize the global style of I' to match that of I'1 and I'(-1). So the global style, right? You have global style consistency being applied to all the keyframes. The keyframes are going from 0 to n, and you're basically saying, okay, well, the very first frame and then the very last frame, and the frame I should be style consistent with the first and the last frame. In Stable Diffusion, each self-attention layer receives the latent feature VI. Okay, so this is the latent image, which I guess is here. Here they called it XI or X0, right? The latent feature X0 in their preliminaries, but then here in their actual section they call it VI. For simplicity, we omit the time step T. Okay, so the latent feature, you're going to have a different latent feature depending on the time step. So there's a couple different dimensions here. There's the dimension of the actual frames, which is n, right? And it's I is the index for n. But then you also have the time dimension within the actual diffusion process. So you have T out of capital T. Linearly projects VI into query key and value. So these are the matrices inside a attention layer to produce the output by self-attention. So here's the actual equation for the attention mechanism, where the queries get multiplied by the keys, and then you end up multiplying. You take the softmax of that, and that tells you how much to get out of each of the values. So wherever the queries and the keys have a high attention, you're going to end up getting a lot of that value. But wherever the keys and the queries do not have a high attention, right, and you can think of the attention as basically just kind of how much agreement there is between those two vectors, right, or how aligned those two vectors are, then the corresponding part of the value matrix is going to not get passed to the next layer. Okay, so they have this VI. You see here how this VI, this latent. Oh my God, this highlighting is terrible. And then you have these matrices here, WQ, WK, WV, and they take this VI and they basically turn it into the actual Q. Pre-trained matrices, where do they get these from? Cross-frame attention, by comparison, uses the key and the values from other frames, and the queries from the original frame. So let's go back to the attention is all you need. I think this is one of the best images in machine learning, to be honest, just because of how popular it is, right? So here you see how this multi-head attention here, this attention mechanism, there's 3 arrows going into it. Those 3 arrows are the Q, the K, and the V, right? And this is self-attention because the Q, the K, and the V are coming from itself, right? Here you have cross-attention. So in cross-attention, the Q and the K are coming from something else, and then the V is coming from yourself. So your cross-attention, it's not the Q and the K, sorry, it's the K and the V. So the K and the V are coming from frame, for example, 1, or frame I-1, the first frame or the last frame, and then the Q is coming from your own frame. Yeah. So here the K and the V are coming from the first and the previous frame, and then the Q is coming from the frame that you're currently on. And that's the cross-frame attention that they're talking about here. And they use these tildes here to indicate. So K prime, V prime versus Q, K, and V without the primes. And it actually it looks like they use the same one here. So you see how this WQ and this WQ are the same. So it's probably the same matrix that does this projection. Intuitively, self-attention can be thought as patch matching and voting within a single frame, while cross-frame attention seeks similar patches and fuses the corresponding patches from other frames. What do they mean by this? Self-attention can be thought as patch matching and voting within a single frame. So whenever you're doing self-attention with a self-attention vision transformer, maybe this? No, I don't think I'm going to find a good picture for this, but basically you're breaking up an image into these patches. So whenever they say patches, think in your head something like this, like just like a little chunk of the image. Whenever you're doing self-attention, you're basically multiplying, you're doing attention between all the patches in an image and then all the patches in the same image. So if there's patches in the image that agree with each other, such as here in this picture, right? If we open this image in new tab, right, you can look at these patches, and this patch and this patch are probably going to be high agreement because they're both pictures of the sky. They kind of have the same information there, so you can expect the attention value for this patch and this patch to be high. You can expect the attention value for this patch and this patch to be high because they're also kind of similar-ish, right? So patch matching, that's the matching that they're talking about, because the patches are paying attention to themselves, and so the ones that are similar to each other are going to activate highly. But it's within the single frame because it's paying attention to itself. And then in cross frame, now you have the same kind of attention mechanism, but instead of this paying attention to itself, you have this, which is one frame, and then you have a different frame. So you're going to be saying, okay, well, the attention between this frame and then a different frame. So if there's specific patches that agree with each other, then those are going to fire. Seeks similar patches and then fuses the corresponding patches from other frames. Meaning the style of I prime will inherit that of I1 and I-1. So this is arbitrary frame, current frame, and then the first frame and the last frame. Shape-aware cross-latent fusion. So cross-frame attention is limited to the global style. They don't do cross-frame attention for local. To constrain the cross-frame local shape and texture consistency, we use optical flow to warp and fuse the latent features. That sounds intense. Let omega ji and mji denote the optical flow and occlusion mask from ij to ii. So the optical flow is W here, and then M is the mask. How did you get this occlusion mask? J and I are indices for two separate frames. Let xti be the latent feature for I prime. Oh my god, dude. What the fuck? Here they're talking about the latent feature vi, and here they change it again and they call it latent feature xi. So that's a little sketchy. They're changing the notation on you. I don't like that. I don't like when you change the notation. You see here latent feature vi, and then here latent feature xti. What do they mean by warp the latent features? I don't know. I think that's what they're going to tell us here. Yeah, it's kind of annoying. For I hat I at time step t, we update the predicted x hat t to 0 in equation by x hat t 0. Okay, so this is the latent. You have the mask. The mask is multiplied by the latent. Okay, so you have some mask, but I think that this mask is not a mask in the image space. I think this M is a mask in the latent space. So you have a mask in the latent space, multiplying this latent, plus 1 minus the mask, so basically the opposite of the mask, everything that isn't masked, times the optical flow, times the latent. What the fuck is optical flow in latent space? Can you even do that? W and M are downsampled to match the resolution of X. So downsampling operation is removed for simplicity. So you're losing, it's probably lossy. We experimentally find that the anchor frame provides better guidance than the previous frame. We observe that interpolating elements in the latent space can often lead to blurring and shape distortion in the late stage. Interpolating elements in the latent space, which is what they're doing here. Therefore, we limit the fusion. So they still haven't really told us what they're doing with this warping. Pixel aware, probably get the optical flow in the image space and then they just downsample. Yeah, that might be what they're doing. Because I feel like you're losing as soon as you go through one attention mechanism, you kind of lose the position, the spatial information, right? That's why everyone constantly passes in position encodings, right? Because you pass in those position encodings, because if you don't pass them in, you're going to lose the spatial information. So if you downsample optical flow, is that going to necessarily align with the latent space? Probably not. How are they getting occlusion masks? I also don't know. I think the occlusion mask might refer to the patches that they're talking about. Let's actually see. Let's finish reading this, because then I think that the only way that we're going to understand is that we're going to read all of this, then we're going to look at the figure, and then maybe we can understand. To constrain the low-level texture features in mid-steps, instead of warping the latent features, we can alternatively warp previous frames and encode them back to the latent space for fusion. However, the lossy autoencoder introduces distortions and color bias that easily accumulate. As far as I know, the spatial transform information are preserved. In the latent? Dude, this is just more confusing. Show an example of the distorted result after encoding and decoding 10 times. Okay, so they take the image, they encode it, and then they decode it, and you should get back the original image. But they show you how you're kind of introducing corruption here. And it's interesting how the error map isn't like is dependent on the content, right? So the encoder and the decoder are lost, or like they're not perfect, but they're not perfect on specific things, such as the edges of here of the face. Fine-tuning the decoder's weights to fit each image, which is impractical for long videos. To efficiently solve, we propose a novel fidelity-oriented zero-shot image encoding method. What? Our key insight is that the amount of information lost each time in the iterative auto-encoding process is consistent. Therefore, we can predict the information loss for compensation. Specifically, for an arbitrary image I, we encode and decode it twice. So you encode the image, then you decode the image, so you get the image back. You have RR, I guess, is twice encoded. We assume the loss from the target lossless X0 to X0R is linear to that from X0R to X0RR. Is that a good assumption? The amount of information lost in the iterative auto-encoding process is consistent? I don't know if that's necessarily true. But that's basically what they're saying here, is they're saying the latent, the error in the two latents after one encode decode is linear to this error in the latents after another encode decode. We define the encoding with compensation. So they're modifying their encoder, and rather than just encoding the image, they're encoding the image into a latent, but then they're also adding this additional term here. And this additional term is the difference in the latent after encoding and decoding again. This is some fucking alchemy right here, right? They're basically doing some weird... They're adjusting. Normally you would just encode the image and you would get a latent, and then you're just going to use that latent to forever for whatever you want. But it seems like they discovered this weird trick where if you add the difference or the error in the latent after encoding and decoding again, you get a better latent, but I don't think this works because of what they're saying. I think actually look at this. So if you look at the error map between this encoder, decoder, encoder, decoder, encoder, decoder 10 times, right? It's kind of the edges, which makes sense, right? Because your encoder and decoder, they're trained to reproduce the image. So they're going to focus their efforts on things that actually matter, like the edges and the specific details. So really what they're doing here is they're kind of saying that the error for the encoder and decoder process has a specific distribution, and that specific error distribution is actually the useful parts of the image latent. So if we add those to the image latent, we probably get a latent that has even more importance on the edges, which ends up being better for video-to-video translation. So this is like a weird little trick. This is extremely weird what they did there. We further add a mask to prevent possible artifacts introduced by compensation, blue artifacts near the eyes. ME indicates whether the error between I and DI is under a predefined threshold. Then our novel fidelity-oriented image encoding takes the form of this. Okay, so the mask here, this ME, is basically some arbitrary threshold that they defined. And whenever they're going to encode the image, not only are they going to basically add to it this random extra term here, which is basically the difference in where the encoder decoder has the most error, which ends up being the areas of the image that have some kind of semantic meaningfulness, you know, like the edges and stuff like that. Then they also multiply it by this kind of threshold mask and get their new latent. So that is some tricky shit right there. This is some alchemy. I don't really like this. I feel like this is kind of weird. Our method preserves image information well, even after encoding and decoding 10 times. Structure guided in painting. For pixel level coherence, we warp the anchor frame and the previous frame to the ith frame. I don't think they're going to explain to us what this warping is. Let's actually look it up. We use optical flow to warp and fuse the latent features. How could you use optical flow to warp images in a video? Frames in a video. What is warping? Let's ask Bard, and then let's also ask GPT, you know. Make sure we don't get a hallucinated answer. And then let's type optical flow warping here. Inverse optical flow. Optical flow is a technique to track the movement of videos. Warping is the process of distorting an image or video by changing its spatial dimensions. This can be done for a variety of reasons. Warping is used to create by moving pixels from one frame to another. Okay, so they're basically just using the optical flow to create a new frame. The displacement of each pixel is used to warp the pixel in the second frame to the corresponding location in the first frame. Yeah, but the problem with this is that you're going to be limited by the quality of your optical flow. So if your optical flow is trash, your warping is actually going to be trash as well. Let's see if this has a different answer. The concept of warping refers to geometrically transforming an image. Transformation can be used to correct distortions. That's not the type of warping they're talking about here. I think this is the estimated to warp the second frame to align it with the first frame. Yeah, so it's kind of using the optical flow to make sure that the frames are basically right on top of each other, but Yeah, kind of what I'm saying here is optical flow is susceptible to errors, particularly in a situation with fast motion. Like any optical flow is just an estimate, it's a guess. So if you're doing warping and assuming that it's going to align, like I'm sure it works well because, or it works okay because each individual frame is very similar to the previous frame, so there's not a ton of motion. But if I were to take the camera and very quickly zoom something by and have a lot of movement and where the optical flow is very big vectors, then this warping would be actually terrible. Yeah, so the bigger the distance between the anchor frame and the previous frame, the more that this warping is actually going to be not a good idea. Overlay them on a rough rendered frame. I bar tilde I. Oh my god. All right, so basically I tilde I minus 1 is your, what's the tilde mean? Is the image, is the keyframe. So this is the warped keyframe, is what the little bar means. So the tilde means keyframe, and then the bar means warped. Without pixel-aware cross-frame latent fusion as M not I, so the mask at time step 0, the mask at the previous frame, the warped previous frame, the opposite of the mask at the previous frame, the, what was this omega here? It was the optical flow, so this is the actual warping of the previous frame, plus 1 minus the original M naught mask. This is no good. Like, you can't be doing this type of stuff with images. Like, this is not going to work for images that are different at all. Like, your images need to be extremely similar in order for you to do this, right? Like, just optical flow, mask out, add optical flow, mask out, right? Like if you look at it here, really fundamentally what they're doing here is they're just adding a bunch of images, right? This is an image here, this is an image here, this is an image here, and all they're doing is they're just straight up adding these images, right? They're multiplying by masks and warping it with the optical flow, but at the end of the day, they're just basically concatenating these things, or adding them, sorry. The resulting fused frame provides pixel reference for the sampling of I prime. We would like I prime to match I prime outside the mask area. So warped frame is with a bar over the I, if you see that, and then fused frame has this tilde over the top. So fused frame is adding together all these warped frames to the original frames. We would like I prime to match I prime outside the mask area and to match the structured guidance. So this is the overlap between these two masks. We formulate it as a structure guided in painting task and follow. Okay, so you have these two masks. They have some overlap. That overlap, you could think of it as a in painting task. And then that defines which part of the latent you're looking at. Okay, so the latents here are in the image space, but the latents here are in the image space masks and then latent space masks. X tilde I t minus 1 is sampled x t minus 1 from x naught, and then they have their fancy encoder here that is basically some weird combination of encoder decoder error. I don't know, I don't like this at all. You know, this is like very kind of hacky. All right, let's see if we can understand a little bit more of this. Framework of the proposed zero-shot text-guided video translation. We adapt pre-trained image diffusion model, blah, blah, blah. So you have your frames. You have I1 to IN. This is your actual video. This is your encoder. Okay, so they're encoding it. They're encoding every single one of the frames. So here you have your latent version of every single one of the frames, which is obviously there's going to be n of those because there's n images. There's going to be n latents. Beautiful girl in Ghibli style, comma. So you see here this comma means that they're feeding in the text and then also the conditioning for the control net. So the way that this is done here, you're actually going to have n of these control net conditionings as well. So you're going to have to feed every single one of these frames through a canny edge detector in order to get a canny edge map for every single one of the frames and then use that. Obviously, the text is going to be the same for every single one of those. Then you have your actual diffusion model, which is going to remove noise from this latent here. And it's going to be conditioning on the text and then also on the control net. Here you have your cross-frame attention. So the diffusion models here are these attention U-nets. So they have an attention mechanism, but they're a U-net, hence the kind of like shape here where it's wider and then it gets narrow and then it gets wider. We haven't gotten to this section yet, but we did read this section, shape-aware latent fusion. So here you have, they show it as the image, but really it's the latent here, x hat, and then x hat I minus 1. So this is the first frame and then some random frame, and then this is the first frame. So they warp that based on the optical flow. So they're basically combining those. That creates this, which is the weird concatenated version, which obviously doesn't look very good at all. This is also the first frame. Pixel aware latent fusion. Oh, here's your actual warp. This is the, yeah, so this is what I'm talking about. It's like this is kind of crap. Oh my god, dude, this is so complicated. Here you have the image at frame 1 and then the image at the current frame. Here you have the decoder. The latent is being fed into the decoder to get the image. The image is being warped with the optical flow. Okay, so this makes more sense. The warping is occurring in the image space, not in the latent space. So they're doing their warping here. Then they're using this warped image, feeding it into the encoder. But this is what's weird, is that the encoder here is not like, if you feed, like the encoder and the decoder are trying to recreate the image. So the image of this person like this is going to be very different from the image of this person that has like these weird like warping artifacts, right? I feel like when you feed this with the weird warping artifacts into this encoder, the encoder is going to try to put in some information into the latent about this weird, like these weird blotches and these weird warp artifacts. So that information is kind of leaking in there, right? And I feel like that could fuck it up. And this is where they're doing their weird encoding image, where they basically encode, decode, and then look at the difference between the encode and the decode, and then add that error to the latent that is produced by the encoder. And then it says here, aggregate. You get every single one of the frames. And then I guess you just keep sampling for every single frame. And here's sampling pipeline. So you go from 0 to time step t. In the beginning, you're doing adaptive latent adjust. Where is that? We don't know what that is. I don't think we've read this yet. Okay. I feel like we kind of understand a little bit better, but it's still very confusing, and it still feels like a lot of the things they're doing are kind of like very arbitrarily chosen. Okay. First, we apply ADA-in to match its channel-wise mean and variance. What is ADA-in? Adaptive something? Arbitrary style transfer, instance normalization to align the mean and the covariance of content features with those of style features. Layer computes a combined feature map that is then fed into a decoder to generate that final stylized image. Okay, so this is probably where they're getting all their weird ideas, right? It's basically here for ADA-in, it seems like basically you can encode this image, and then the decoder should reconstruct this image, but you can also feed this image, and it's going to result in a different latent, right? This and this. VGG is an old type of neural network architecture. It's basically like a ConvNet. So you're kind of getting the encoder, the encoded features, or a vector that represents this image and a vector that represents this image, and ADA-in basically combines those in an intelligent way. It seems is basically what's going on here. And you have probably a consistency loss and a style loss, and you have to trade off in between those. Okay. We apply ADA-in to x hat. There's too many x's. Which one is x hat? So x. We have x tilde, we have x hat, and we have x. Do you guys remember what x hat and x tilde were? I don't. So x hat here, the latent feature at time step t, and then x hat is the result of the shape-aware cross-frame latent fusion. So that's what x hat is the output of that. So the output of the shape-aware cross-latent fusion is fed into this ADA-IN. Oh my god, dude. That is so gross. For frames with similar content, existing video frame interpolation algorithms are capable of generating plausible results by propagating the rendered keyframes to their neighbors efficiently. However, compared to diffusion model, frame interpolation cannot create new content. To balance between quality and efficiency, we apply our adaptive diffusion models to the keyframes only. We then adopt a patch-based frame interpolation algorithm to render the remaining frames based on coherent keyframes. What is this? Stylizing video by example, 2019 paper. So that's how they're actually getting every single frame. So they're really only doing this for the keyframes, and then they basically use this other random paper here to make every single frame. We sample the keyframes from the video uniformly for every k frames. The keyframes are denoted I0, IK, I2K, and are rendered to I'0, I''K, I'2K. Taking the first k frames, for example, we interpolate. I see here they go. They switched again. You know, it's like here they use n to refer to the keyframes, and then here they use k to refer to the keyframes. I don't like this. Is a very bad habit. You don't want to be changing your definitions like that constantly. taking the first keyframes, we interpolate I hat or I1, I k minus 1 with I prime 0 and I prime typo here again. There's no I. See that? It should have been an I prime k. Dude, this paper is littered with typos. First, we use patch-based propagation to propagate I prime 0 and obtain intermediate frames I prime 1 0, I prime k minus 1 0. Likewise, we propagate I prime k and obtain I prime 1 k, which should be similar-ish to I prime k, k minus 1. We then adopt the temporal aware blending to blend to get the final result. So not only is this technique that they're doing incredibly complicated and has all these pieces, but one of these steps is actually, like every single one of these little steps is actually even more intense. Yeah, so this section here, this ADAIN, like if you were to zoom into this little brick right here, it's actually composed of like 3 other little bricks that are inside there, right? Like if we actually go to ADAIN, it's actually this. So this is just not, there's nothing simple about this. There's nothing simple about this approach. This approach is incredibly complicated. Yeah, like this here is here as well. So just look at the amount of encoder and decoder steps that they have to do, right? So here they're encoding every single frame. Here they're, in this ADAIN, you also have an encoder and a decoder as well. Here, in the whenever they actually do the encoder, they're saying that they encode and decode twice. So they encode and decode, and then they encode and decode to get this error between the encoder and decoder. So the amount of encodings and decoding steps is huge, right? Because they do it like at least like a couple times for every single frame. So that's a lot of model inferences, a lot of, every time you have to encode it, you have to run inference. Every time you decode, you have to run inference. So this is very computationally intensive. We adopt a guided path matching algorithm with color, position, edge, and temporal guidance for dense correspondent prediction. Is their approach really efficient in the perspective of time? Probably not, because if you have an approach that has a lot of inference, but the inference can be batched, then you're fine, because you can just batch it, and you can do it in less time, right? But everything that they're doing is based on some other thing, right? It's like they can't encode this frame until they've encoded another frame, because it has to be conditioned on this other thing, right? It's like every single one of their little steps here is dependent on a previous step. So basically everything is waiting on something else, so you can't do this all in parallel. You have to basically do it sequentially. And that's why it's going to be so slow, because not only is it very complicated with a lot of steps, but you have to basically do all of these steps in sequence. Yeah, it has to be in sequence. I don't know much about this ADAIN, but I assume it's also in sequence. Main idea of the blending of I prime I0 and I prime IK is to combine them with a pixel selection mask MI based on the patch matching error. MI comes from a minimum error mask M hat I, denoting the region where the patch matching error is lower on I prime 0 than I k prime 0. So this mask is based on patch matching error. So they take 2 consecutive frames, right? So they're trying to blend these 2 frames here, this frame and this frame. And they're saying, okay, if I'm going to pick a random patch from that, and if these 2 patches are very similar, then the patch matching error is going to be very low, which means that I'm going to mask that out. So I'm only going to focus on the patches where the error is high. To preserve the temporal consistency, M0 starts from an all one matrix, right? So a mask that is all ones is not going to do anything, but a mask where you have a 0 is going to zero out that thing, right? So masks are binary. They're basically 1 or 0. The previous mask is warped to an initial M. Here you go, warping masks with optical flow. Like, that doesn't sound like a good idea. Then only the pixels satisfy are allowed to update. M hat or M bar IP to obtain MI. This measure can prevent pixel selecting the next keyframe from turning back to the previous keyframe. The blended frame serves as the historical histogram reference for contrast preserving blending to obtain the final result. We do not apply Poisson diffusion, Poisson fusion, which we sometimes blurs the textures and causes flickers around the keyframe. Visual comparison with zero shot. So, I mean, this is just an ablation study here. Okay, so, I mean, that's the end of their experiment section here. I don't feel like I understand this, to be honest. I'm just going to be honest with you guys. There's a lot of pieces here. It kind of seems like they threw the kitchen sink at this and they tried every single weird additional loss that they could. Or it's not a loss because they're not pushing gradients, but every single weird constraint. They have like, what is this? 1, 2, 3, 4, 5. 5 different weird interpolations. The thing I don't like the most is these weird interpolations that they're doing here, these warps, where they're basically taking these masks that are based on patch error and then using those to basically warp frames into other frames. Right? And kind of the reason I don't like that is kind of what I was explaining earlier, and it's because that only works if subsequent frames are the same, right, or very similar, and that's only the case if you have a very slow video where nothing really changes. If you have, for example, imagine if you have like a scene change in a movie where like the scene suddenly changes. Imagine if that scene change happens to fall exactly on one of these interpolated states, right? They're not doing anything fancy. They're not figuring out, they're just assuming that these frames are all going to be consistent with each other, right? They're just kind of like breaking it up into keyframes, and those are the keyframes. So this is a very fragile approach, I think. I think it's just there's a lot of pieces here. They're very fragile to the fact that the frames need to be consistent with each other. I think this could be cool, but like the kind of weirdness of adding it is strange. This like encoding the image, but then adding the error of the encoding process, where the error is defined by the difference between encoding and decoding and encoding and decoding again. I don't know, guys. This is not giving me any confidence for sure. The experiment is conducted on one NVIDIA Tesla V100. Okay, so another reason that people choose to do experiments and papers where it's a zero-shot technique is because you don't need a train, right? So if you're working in a university setting, you don't have potentially the type of compute budget that a Facebook AI researcher has. So if you can find some kind of research project that doesn't involve fine-tuning or training, you're probably going to be able to do it with a single GPU. So part of this paper and the fact that they really don't want to fine-tune is because they probably only had one GPU, right? This makes it sound like it's just one guy. He was sitting there, he had one GPU, and that's it. We employ the fine-tuned LoRa models from Stable Diffusion 1.5. Stable Diffusion originally uses 1,000 steps, but obviously that's really intense, so they're probably not going to do that. By default, we set TS equals 0.1 T max, TP0 0.5 T max, TP1 0.8. So, okay, so they're basically choosing 1, 2, 3, and 4. So rather than 1,000 diffusion steps, they're doing 4 diffusion steps. Structure guidance with the control weight tuned for each video. So the control weight is what determines how much the text embedding is influencing the diffusion. So having to tune that for each video is also not great. We use GM flow for optical flow estimation. So here's how they're actually getting their optical flow, right? And remember that optical flow is not perfect, so any technique you use to get optical flow, there's going to be some error there. I guess this is the paper that they used. No, it's this one. GM flow optical flow. GM flow optical flow. So this is how GM flow optical flow works. It's basically, it seems like a deep learning transformer based situation. You give it 2 frames and it'll give you the optical flow image, right? Where the color represents the direction of the flow. Here you go. So they have the control net, of course, and then they have GM flow here. So this is the actual optical flow that they're using, which is, I guess, also using PyTorch, so that's good. But look at all this crap. Look at all these extra parameters here. Max flow. Upsample factor. Num scales. FFN dim expansion. Like, every single one of their little additional modules that they just kind of like say, oh, we use GM flow. Like, well, GM flow has a ton of extra parameters, a ton of settings. Like, what did you pick for those settings, right? So that's kind of one of the negatives of doing all these these complicated systems, that you just get the amount of hyperparameters just explodes and it gets out of control. Okay, they're sampling keyframes every 10 frames. Videos are resized to 512 by 512. Keyframe and non-keyframe translations take about 14 seconds per frame. So 14 seconds per keyframe and then 1 second per frame. Full video translation takes about 1.14 times K. I mean, can you just multiply that out for me? What's the number? K equals 5. We will release code upon publication of the paper. Where's the code? ¿Dónde está code? The official code of the first 3 methods does not support control net. Okay, so here they're comparing against these. Figure 5 and 6 represent the visual results. Fate 0 successfully reconstructs the input frame but fails to adjust it to match the prompt. Vid2Vid0 and Pix2Video excessively modify the input frame, leading to significant shape distortion and discontinuity across frames. While each frame generated by Text2Video0 exhibits high quality, they lack coherence and local textures. Our proposed method demonstrates clear superiority in terms of output quality, content and prompt matching, and temporal consistency. Conduct a user study with 23 participants. So, I mean, that's good. You know, user studies are good. I like that. How well the result balance, blah, blah, blah. Overall quality. Ablation study. Okay, so they're going to get rid of different little pieces here. Hierarchical cross-frame consistency constraints. Figure 7 compares the results with and without different cross-frame consistency constraints. We demonstrate the efficacy of our approach on video containing simple translational motion in the first half and complex 3D rotation transformations in the second half. Yeah, this is, I think, the more interesting thing. Is like, how are you going to be able to deal with that? It's not even complex. So they're saying complex rotation. Like, is this really complex? Like a person literally turning their face is complex? Like, what about a video where you're looking at something and then you like switch and look at something else and then switch and look at something else? I feel like that's what complex means. These are still super easy. Okay. So here's the baseline. So the full model plus the cross frame attention. Kind of feels like it's about the same. Plus this extra ADIN, ADAIN. Kind of also seems pretty much the same. Plus SA Fusion. Consistent hairstyles. Neck ring translates with neck. Acne is preserved. Image diffusion models renders each frame. Cross-frame attention keeps overall style consistent. ADIN preserves the hair color. Shape-aware latent fusion keeps the overall movement of the objects coherent. And pixel-aware latent fusion achieves pixel-level temporal consistency. Effect of pixel-aware latent fusion on frame propagation. So you have different frames. Pixel level consistency between keyframes leads to ghosting artifacts on the non-keyframes during the frame blending. So maybe don't do frame blending, you won't get ghosting. Effect of the pixel-aware latent fusion, arcane style, a handsome man, loving Vincent, hiking grass. So this is, Arcane is like a TV show. So it's kind of like a Pixar type thing where it's like a specific visual style. Here they're kind of showing you that you lose the little staircase here. Right, you have a real image and then you're kind of trying to make it a Van Gogh image and you get this little staircase in frame 1, and without this fusion, this pixel-aware latent fusion, the staircase kind of disappears, but with the pixel-aware latent fusion you maintain that little, whatever this is, little staircase. So more pixel consistency. Let's look at these ones. User preference rates. Damn, overwhelming preference for this. So, I mean, their technique is undeniably good, right? It does seem like people, the results are good and people like the results. But my main problem with this is just the complexity and the amount of different things in this technique. But the results are good. They're undeniably good for sure. Like 64, 67% preference compared to basically low single-digit preference for the other techniques. Fidelity-oriented image encoding. We present a detailed analysis of our fidelity-oriented image encoding. This is the weird thing where they were looking at the error between the encoding and decoding multiple steps in a row, and then adding that to the encoded latent space. Stable Diffusion has whatever autoencoders. So this is the actual autoencoder, this variational autoencoder here. effectively alleviates these issues. For quantitative evaluation, we report the MSE between the input image and the reconstructed result after multiple encoding and decoding. Using the first 1,000 images of MS Coco. The results are consistent with the visual observations. Our proposed method significantly reduces error accumulation compared to raw encoding methods. They indeed solve the flickering problem. Yeah, I mean it's definitely impressive, you know. Let's go to the actual thing. I just think that someone's going to figure out how to do this in a cleaner way. You know what I'm saying? Let's actually go to their website. I had it up, but it got deleted. Here we go. Yeah, like this is the best. But it's also like this is a very simple video, you know, it's like you're just kind of sitting there. Nothing's really changing, and I think all their videos are kind of like that. Yeah, every single one of their videos, there's very little change. It's just basically a bunch of frames that are very slowly moving, right? So even though their technique works very well, it's limited to this specific type of video that's very simple, and then even then it's very complicated, so I don't know how many people are ever going to use this, or certainly not build on top of it, right? Like there's so much stuff in here already that imagine trying to build on top of this and add even more stuff. So I think what's likely to happen is we're likely to see a technique that has different priors and different kind of assumptions and is much simpler and works for videos that are more have more motion, have more complexity to them. But we might not see that for a couple years, you know. So I don't know, this might be the way to do videos for a while. We validate our encoding method in the video translation process. Our method mostly reduces the loss of detail and the color bias caused by lossy encoding. Yeah, so it's almost like they're basically this entire fidelity-oriented image encoding is a way to deal with the fact that these image encoders care more about the semantic information in an image than the visual appearance of an image. In fact, most image encoders are kind of almost encouraged to not pay attention to the visual appearance, usually because they use forms of data augmentation when they're actually being trained. So it's kind of interesting how this particular task is a task where you want encoders and image representations that are very, very specific about the appearance. Flexible structure and color control. Flexible control over content preservation. Rather than setting x of t, which is the very first, to a Gaussian noise, which is what you do in normal text-to-image generation, we use a noisy, latent version of the input frame to better preserve details. If the input frame introduces unwanted color bias, a color correction option is provided. The input frame is adjusted to match the color histogram of the frame generated by x of t. Even more complexity. With the adjusted frame as input, the rendered results better match the color indicated by the prompt. Limitations. Illustrate typical failure cases of our method, figures 17 and 19. Failure to optical flow due to large motions. Okay, that's exactly what we've been talking about. And this isn't even that big of a large motion, right? It's like you're just literally rotating. Trade-off between content and prompt. So here's the ghosting, which I guess is introduced by the blending of these frames. We find smaller details and subtle motions like accessories and eye movement cannot be well preserved. During the translation, we uniformly sample the keyframes, which is not optimal. Yes, ideally you would want to pick keyframes that are content aware, like semantically aware of like what, or aware of whatever is in the image. So a keyframe on a scene switch, for example. One potential solution is user interactive translation, where users can manually assign keyframes. How much more annoying would that be? This paper presents a zero-shot framework to adapt image diffusion models for video translation. Our method utilizes hierarchical cross-frame constraints to enforce temporal consistency in both global style and low-level features, leveraging the key optical flow. The compatibility with existing image diffusion techniques indicates that our DIA might be applied to other text-guided video editing tasks, such as video super resolution and inpainting. Additionally, our proposed fidelity-oriented image encoding could benefit existing diffusion-based models. Yeah, this is the more interesting one. You know, it's like there's something here. We believe that the approach can facilitate the creation of high-quality and temporally coherent videos and inspire future further research. Yeah. Okay. So that was a hard paper to get through, you know? Very intense. But let's see if we can try to summarize this. So let's take a nice sip and then... Okay. So today we reviewed a paper called Rerender a Video. This is a zero-shot text-guided video-to-video translation paper. So given an input video and some text, can you create a new video? So the important thing that they did here is that they started from the design requirement of zero shot, where they didn't want to train anything, they didn't want to push additional gradients, and they wanted their technique to be kind of agnostic to the diffusion model that's used, which they achieved. They did do that. This technique, it doesn't really depend on the diffusion model, and you can also apply LoRa and ControlNet and whatever extra crap you want to your diffusion model, and it still works fine. However, there's a lot of things that I did not like about this paper. So one thing is they have a ton of typos. So they have a typo here. They need a D decoder. They kind of switch the notation constantly, where they use different variables to represent the same things depending on the section. And I think, to me, the biggest negative of this paper is just how complicated it is. Like, there's so many different things here. Like, they have 5 or 6 different little tricks that they use, right? They are taking these frames, they're getting optical flow using some external optical flow that's also deep learning based. Then they're basically interpolating between these frames, they're warping between these frames. They have these masks that are based on these patch errors. And the final result is very good. You know, like, these results are very, very clean. They solve the flickering issue, but they kind of make a deal with the devil to do that. You know, it's like the amount of complexity they introduce in order to get this result is huge. And at the end of the day, they really only achieve that result for basically 1-second videos where everything is basically the same. You know, they talk a lot about local consistency and global consistency, but if your video is just a 1-second video of a person tilting their head, is there really much of a difference between global consistency and local consistency? They're kind of, you know, like, what is local, what is global, if pretty much the thing is motionless, you know? Like, you know, the eyes are pretty much in the same exact place the entire time. The nose is pretty much in the same exact place the entire time. So, like, I don't feel like there's a huge difference between global and local there. One thing that I did find interesting, I don't like, so they introduced this fidelity-oriented image encoding, where they noticed that whenever you encode an image and then decode that latent back into an image, there's a little bit of an error, right? Which you could have guessed that, right? Of course, encoding and decoding is going to be kind of lossy. But the interesting thing that they realize is that the error in the encoding decoding process is not like Gaussian noise, right? It's not like you take the image out of your decoder, compare it to the original image, and you get basically some like noise looking thing. What you actually end up realizing is that the error in the encoder decoder process is in a way highlighting what's important in the image, right? So here's the error map of this decoder and encoding process applied 10 times in a row, and you can see how it actually kind of tells you a little bit about what's important in the image. It's informing you about the content of the image. So they do this little trick here where they basically say, okay, well, rather than just encoding the image, we're going to encode the image, but then we're going to also add what they're calling here this encoding compensation or whatever, like let's see if they have an actual error term. I don't know what they call it, but they add this error term, and I feel like that's actually a very clever way of taking your latent representation, which represents your image, and then adding to it kind of almost like amplifying the specific parts of that latent that represent the edges of the face, the eyes, the nose, and the mouth. So it like it gives you an encoding function that is better at paying attention to the things that end up mattering, if that makes sense. So this is actually kind of cool, and I wonder if other people are going to take this concept and use it in their own research, because this concept isn't necessarily limited to this specific approach. So this is one of the cooler kind of little pieces of this paper, is this fidelity-oriented image encoding, which seems kind of arbitrary, but it kind of works. And yeah, what else? In terms of the results, it's very good. Yeah, they do a user study, which is kind of the gold standard in terms of image generation and video-to-video quality. And people seem to overwhelmingly prefer this approach to already existing approaches. And yeah, that's kind of basically it. Kind of a cool paper, you know, but very complicated, and the kind of math section is a little bit sketchy. But there's some gems in here. I think this gem, the fidelity-oriented image encoding, is a gem, and then of course the most impressive part is the results. But yeah, that's Rerender a Video. That was a tough one for sure. Thanks, chat, for helping me get through that. Thanks, Hyun Ho. Thanks, Keyshawn. Thanks, Erland. Hopefully you guys got something out of that. If not, arbitrary but kind of works is, I heard that a lot lately. Yeah, because I think that there's one way to get noticed is to create, make something that the demo is good, right? So this is a paper where they just want to make the best possible demo, which is this, right? The best possible video to video, but they don't care about the how complex it is and the algorithmic algorithm behind it, right? There's other papers where they're really just trying to find a very simple algorithm, a very simple kind of approach of doing things that makes you feel warm and fuzzy inside. So it's like you kind of get to pick and choose. It's either you want the demo to look cool or you want this architecture diagram to look cool, right? And here they very clearly wanted the demo to look cool, and as a result, the architecture diagram looks like a giant tangle of crap. But in other papers, the architecture diagram looks cool and intuitive, and then the demo actually kind of looks kind of shite. So cool. That's it. They apparently have a Hugging Face demo, so you can drag and drop videos in here, and then I guess it'll output. Here's some examples. But yeah, go ahead and try it. Figure out whether the hype is worth it. If not, see you guys tomorrow. I think we're doing a NLP paper tomorrow. So it's going to be more about language models rather than diffusion models. But if not, thank you. Thanks for listening. Like and subscribe. See you guys tomorrow.